All right, let's go. Welcome to Just Enough Assembly for Compiler Explorer. My name is Anders, and I work in Norway in Zivid, where we make these cool robot eyes, where I mostly do C++. I also run this quiz site called CppCquiz.org, which is a C++ quiz site, and I hang out on Twitter a bunch on these various accounts. So if you want to talk to me later, you can find me on Twitter. But we're not here to talk about any of that. We're here to talk about Compiler Explorer. And what's so cool about Compiler Explorer? It's a web page where you can paste your C or C++ or Rust or whatever on one side. And then on the other side, you can see the assembly code that gets generated. And why is it interesting to look at assembly code in 2021? Well, it's interesting because you write your C++ code for humans to read, right? And then the compiler translates that into some machine code, which it then passes to the CPU to execute. And for each machine code instruction, there is a corresponding assembly instruction. And if you can read the assembly, then you know what the compiler did to your code. You know exactly what's going to be run on the CPU. And the good thing about Compiler Explorer also is that you can try out different compilers, different compiler options, and you can compare what code gets generated. But instead of just talking about it, let's actually have a quick look at the site. So this is Compiler Explorer. I need to hide a couple of windows here, and then we can get going. So here you can see I just typed in some source code to the left, just some random code. Don't look at it, it's not important. It's just for to have an example. And then you can see to the right, you can see some assembly code. And that's what GCC 11.2 decided to generate. Then I can select from a host of different other compilers here. I can give it different compiler options. And you can also see it has some like practical extra features, like it's annotating the code so I can see. So here's this computer function over here. And like all of this is coming from the computer function. Then you have the caller function, and all of this comes from this caller function. And you can also see that when I'm moving the cursor around here, you can also see on the other tab, you can see like which part of the C++ code corresponds to which parts of the assembly code. And it's also doing some syntax highlighting, and you can like hover over instructions to get some pop-up tips. And it's really lots of useful features. And there's a lot of stuff going on here in the assembly code. And in 50 minutes or so, we are going to understand everything in that pane over there. And that's not because I'm going to go fast. I'm going to do this really slowly from the beginning. And in 50 minutes or so, we're going to understand what all of this means and also why it's there. So why are all these things up here? So I need to switch a window again and look at the poll. So I posted a poll here asking about people's experience with Compiler Explorer. And it's a really good distribution from none or I've heard of it until I use it all the time. So hopefully there will be something to learn from everyone. This is a very basic talk, but maybe even though you use it all the time, maybe there are some details you've been wondering about in the assembly code. So hopefully there's something to learn for everyone here. If you have any questions during the talk, then there's a Q&A feature here in Zoom. So this is one of the first talks in CppCon this year, so maybe you haven't all used it, but there is a Q&A feature where you can post your questions, and then I get them in a separate window, and I can keep track of which ones I've answered and not. So please use that, especially if you have questions about what we're currently talking about. So if something is unclear on the slides, something like that, then ask it right away. If you have other questions of the type, like I'd also like to know some more about this other thing, it would be good to wait until the end of the talk, because then it's easier to make sure I can answer to the more urgent questions as we go. Right, that's it for the intro. So let's just dive into the content itself. And almost all the slides today are going to be like slideware toy X86 emulator kind of thing. So in the middle of the slide, you'll see the CPU, and inside of the CPU, there are a bunch of registers. So in order to do anything interesting with data, you have to get that data into some registers, right? So for each example, I am going to visualize the registers that are interesting for that particular example. This is the first example. You see the CPU here in the middle, and I'm showing two registers, RDI and RSI, which are the ones I'm going to use in this example. I'm displaying the contents of each register here in hex, because that's just a convenient way to look at data. And for each example, I initialize the registers to 0. And that's not happening in reality. So in reality, registers are they just have whatever was there from before. But just to make it easier to follow the examples, they are always initialized to 0 at the beginning of each example. So let's get some assembly code up here to the left. That's where you'll see the assembly code on all of my slides. And assembly is a very simple language in the way that it's just one line of instructions and of instruction after the other. So you have the instruction to the left, and then you have 0 or more operands to each instruction. And I also put up this little orange debugger indicator kind of thing, so we can like step through the code like this, just as in a normal debugger. And then we can visualize what's going on inside of the CPU. So if we start on this first instruction, that's a move instruction. And just like in C++, move does not mean move. So in assembly, move means copy. So it means to copy one of the operands into the other. And in this talk, on the slides, I'm using the Intel assembly syntax. And that's because I find it more readable, and it seems to be the popular option these days. So we're using Intel assembly syntax here, and in that syntax, the second operand to move goes into the first one. So move RDI2 means to take the immediate value 2 and put it into the register RDI. So let's just execute that instruction, and then we got a 2 here over in RDI. The next instruction is move RSI4, and then you can guess that this is going to put the value 4 into the register RSI. So let's execute it, and we see we got the value 4 in that register. The third instruction here is a new one, it's add. And add does actually add, no surprise. The only quirk thing here is that we're used to in our high-level languages to go auto result equals A plus B. In assembly, there is no result involved. It's just it's adding these two numbers, or these two operands, RDI and RSI, and the result goes in the first operand. So it takes RDI plus RSI and stick it into RDI. So this is more like a plus equals kind of thing. So we're going to add 2 and 4, and that ends up here in the first operand RDI as the value 6, the sum of those two numbers. That was registers, but we only have like a limited amount of registers, and they're not very big. So of course, if you're going to do anything interesting, we are going to need some memory as well. And I'm on X86. This talk is about X86 assembly. And on X86, the stack grows downwards. So I've visualized a bunch of memory here to the right, and you can see I've put like 1 byte on each line and displaying in hex again. And then I have the memory address to the left of it. And I'm just saving some space. I'm only displaying like the last 2 bytes of the address to not just have a 64-bit address, would be too long. So you can see you have B3 up here and A0 down here. So the low addresses are down here and the high addresses are at the top. And then our stack will have been growing downwards like this from above. So the top of the stack is then actually here. And when we move stuff, it's going to grow downwards. There's also one more new register here called RSP, which is the stack pointer. And the stack pointer just tells you what is the current top of the stack. So as soon as you push something on the stack, that's going to change. So you can see RSP holds the value B0. So B0 is currently the top of our stack. And I also put this little RSP pointer over here just to visualize what RSP is pointing to. So here is our current top of the stack. So let's then start by putting just a big number into RDI. So we're seeing move again, move this immediate value into RDI. And it just has a bunch of bytes that are different, so we can recognize which byte is which later. So nothing special about that value. Then I want to start using the stack, and I want to push and pop stuff onto the stack. And all of my slides today are going to use the stack. But push and pop is like, that's a stack thing. But all the other things we see about stack addressing or memory addressing all will be the same for the heap and for global variables or global memory and everything like that. So even though we're just seeing the stack here, all the memory addressing is just general addressing, which is the same all over. But one thing you can do in particular on the stack is pushing and popping. So the first thing we do here is to push RDI onto the stack. And you can see now this instruction has only one operand, which is which register to push. And then you don't have to say anything about how many bytes do you want to push, where do you want to push it. It just pushes it at the top of the stack and then increments the stack pointer to follow along. So the first question then is, how many bytes am I going to fill up over here in the stack? And this being an online talk, it's not very interactive, but if you have made up your minds, the answer is 8, because we are on a 64-bit architecture. RDI is a 64-bit register, and we're going to put 8 bytes onto the stack. So that means these 8 bytes here. And the only remaining question then is, what will be in this byte here? So there are 2 plausible answers to that question. You could put the 10 over here, or you could put the FE over here. So the question is about byte ordering. And since we are on X86, which is a little endian architecture, that means that the least significant byte in a number goes on the lowest memory address. So when we push this on, let's just push it on now, execute the next line, push RDI. And we saw that we got the number in here with the least significant bytes on the lowest memory address. There's a question in chat, is this presentation teaching assembly or compiler explorer? So the title of the session is just enough assembly for compiler explorer. So the presentation is teaching the assembly the assembly background you need to understand what's going on compiler explorer. I hope that answers the question. So we're going to go through some basic assembly in the beginning, and then we'll go to compiler explorer, and we're going to bring some examples from compiler explorer back into this emulator thing to see what happens on the site. But specifically, we're teaching enough assembly to understand compiler explorer. Right, so now we pushed those 8 bytes onto the stack, and we saw that also here the stack pointer has been bumped 8 bytes along. So if you push more stuff, then we will push it further down here on the stack. The next thing we can do then is to pop again from the stack. So pop RSI will then pop into RSI. So again, we don't have to say how many bytes, where to pop it from. It's going to pop from the top of the stack and into the RSI register like this. So then all these bytes here from the stack got copied into RSI, and the stack pointer got moved back up here. Now, we can, of course, also address memory, because pushing and popping on the stack is useful in some cases, and you can actually do quite some stuff with just like a little stack machine. But we want to be able to arbitrarily address memory. And all of this also applies then to the heap or to globals or whatever. So if we first just put some values into RSI and RDI, a bunch of 3s in RSI and a bunch of 2s in RDI, then we have a move instruction again. And you see the comma over here. So again, we have 2 operands. We have this operand, and we have this operand. So the RSI, that's obvious now, hopefully, that you're going to take something from RSI and put it into something. But what is this something? It's keyword putter RSP -8. So the expression in, so someone is raising their hand. I think if you could use the Q&A thing, if you have questions, that would be good. I don't think we're supposed to do any talking during the talk. So just use the Q&A thing, and I'll try to get to it there. So inside of these square brackets, we have RSP minus 8. So that's an expression that we want to compute, and then that is an address of something that we're going to use. So we have RSP minus 8. So here's RSP minus 8. That's down here. So we're going to move something in here. And this expression is then, the value of this expression is A8. And and that's just like a number. So we kind of have to dereference it like a pointer. And the way we do that is by saying keyword putter. So that's a quad word pointer where you have a byte, which is 8 bits. Then you have a word, which is 16. Double word is 32. And a quad word or a keyword here is 64 bits. So we're just dereferencing this value of A8 to say where we're going to put this value. So then we take the value from RSI, which is all these 3s, and put it into this that we saw over here. Execute that, and we get all these 3s into memory. And there's the question. How does pop know how much to pop from the stack? Well, if you specify a 64-bit register, then you say pop RDI. RDI is a 64-bit register, so we're going to pop off 8 bytes. If you said like pop EDI, for instance, which is a 32-bit one, then you'll just pop off 4 bytes. Then the next instruction is the add instruction, and it's exactly the same syntax here again. So we're going to do RSP minus 8, which is A8, and then dereference that, and then we get the value. So we don't take the value A8. We have this keyword putter saying dereference this and get the value which is stored here and put that into RDI. So if we execute that one, not put it into, sorry, this was the add instruction. So we add RDI with whatever we got over here from the memory. So we have all these 2s in the register added to all the 3s in the memory, and then we get 55555 stored in RDI, but because again, add stores the result in the first operand. And the thing we saw over here, this is exactly how a local variable would look like. So if you have a function and you say long L equals a bunch of 3s, then this is exactly how it would look like in Compiler Explorer, for instance. You could, or on your CPU and during execution as well. So you'll have all these 3s here on the stack. Keyword putter means I'm going to use to dereference this. So it's just a syntax to say that I want not the value from this expression here, but I want whatever this is pointing to. Okay, so RSP minus 8 here, that will be the address, that will be E8. So the value of this is E8, but like you can think of this as whatever is stored at E8. Kind of, it's sort of like dereferencing it. So then we know how to read and write local variables. We wrote a local variable in here, and then we read it again for use in this add operand. All right, so now we're starting to get some like real C or C++ code in here. Oh yeah, I forgot to read the question. Yeah, sorry. The question was why we have this keyword putter thing in front. And then someone's saying, yeah, only one operand can be the memory. That's also correct. You can't have can't have both the operands being memory. But let's move on. I wanted to just have a little short talk about register sizes before we move on. In the original AT86, we had the AX register, which was 16 bits. And then we had just names AH and AL to refer to the low and high parts of that. So we have 2 bytes here in AX. You could refer to those bytes individually by AH for the high byte or L for the low byte. But it was still the same register. So if you write to AL, you're actually writing into the lower part of AX. Then the 386 came along, gave us 32-bit registers. So we got EAX, but again, you have these as like synonyms for the lower parts of EAX. And then finally, in the 64-bit architecture, we got the RAX registers. So coming back to the previous question again, if I say pop EAX, I'm only going to pop into this part of RAX, and then I only need to pop 4 bytes. And then the question, next question is, how big is an int? And again, very little interaction in a talk like this, but what's the size of int? And of course, the answer is that it's not defined anywhere. It's up to the implementation, really. But on my computer, which is a 64-bit architecture, the answer is then 32. Yeah, it depends on the toolchain as well. So on my like regular Ubuntu Linux thing with GCC and like all the defaults, I have 32-bit ints. When they went from 32 to 64-bit registers and architectures, they could have just doubled the size of all the ints, but yeah, that was would be a bad idea. So we just still have 32-bit ints. So which types can fit in these registers? Well, in the big RAX, 64 bits, you can put your signed or unsigned longs. In EAX, you can put your signed or unsigned ints. In AX, you can put your signed or unsigned shorts, which are 16 bits. And then in this AH and AL, you can put your 8-bit signed, unsigned, or just plain chars. So let's try to do the same example again, exactly as before, but using now the 32-bit versions instead. So this is how ints would look like, and ints are popular. So let's look at ints. Just put some values in again. Now we put them in ESI and EDI. So let's run those two. Now you can see we only wrote to the lower half of this register, these registers. But we still see the full register here. Just it's nicer for seeing what's going on. And then we can see that when you're going to move stuff into memory, we now move ESI instead of RSI. And I'm using D word putter instead of Q word putter for double word, which is a 32-bit value. And then I decided I want to put it just -4 from RSP instead of -8, as I had on the previous slide, because I just want it here at the top of my stack frame. So I put ESI, that's all these 3s, into RSP -4, and I get them over here. And then I can, of course, add it again like I did on the previous slide. So I have RSP -4, these ones, add those to EDI. So EDI has a bunch of 2s. We add the 3s from memory, and we get all the 5s in the first operand, which is EDI, and we get all the 5s in here. Now we know also how to read and write ints. But we don't want to just write single ints or longs or bytes or whatever. We also need to have arrays. And arrays is also a really good motivation for looking at some more advanced memory addressing. So let's first start with putting some bytes in memory. And now I'm using 16 bits values just for some variation and to save some space on the slides. I'm going to put a bunch of 1s, 2s, 3s, and 4s at RSP -8. The 1s in here, 2s in here, the 3s, and then the 4s into memory. And then I am going to treat this as an array, because assembly doesn't have types. So these are just some bytes in memory. So these could be like one big long. They could be 8 separate bytes. They could be like an employee record or part of a network packet, or like assembly doesn't care. There's no types. So we just have to decide that, well, for our purposes, we're going to treat this in this example as 4 16-bit values. So an array of 4 values. And anyone who's done a bit of C and C++ know that arrays, they are like almost just pointers, right? Anytime you do something with an array, it's more or less just a pointer to the first element. And that's exactly what assembly thinks of that matter as well. So to deal with arrays in assembly, you need a pointer to the first element. And our first element here is at RSP -8. So here is RSP -8. That's our first element. So if you want to do something, then you want to load that address into a register. And so we want to put A8 in a register as the base pointer of this array. But you can't just move this into a register, because then you move the value. What you want to do is you want to use the instruction called load effective address, or LEA. And load effective address, again, just does the regular address computation that we saw before. RSP minus 8, that's now A8. And then instead of dereferencing that value, it says, well, store that address itself into some register. And let's just use RDI now for storing that. All right, so now we say load effective address RSP minus 8, that's A8, put it into RDI. If we execute that, now RDI has the value A8, and that's now a pointer to the beginning of the bytes that we decided are an array. And now I want to access, say, the fourth element in this array, or if you like, it's 0 based, so the third element, if you start counting from 0. And then you need to if the base is here, you need to step over like 1, 2, oops, draw. So 1, 2, 3. So here is our fourth element, or the third if you count from 0. And then you have to multiply that with the size of each element. So that means 6. Like 3 elements up, and there are 2 bytes each. So RDI plus 6. Then you can dereference that. Yeah, why do we use LEA instead of move? Yeah, that's a good question. If we had used move, we would have had in RDI the value stored at RSP minus 8. So if you had said move RDI, you would have to also put the putter thing here for it to compile. Then we would have like 1, 1, 1, 1, 2, 2, 2, 3, 3, 3, 3, 4, 4, 4, 4. But LEA just takes this address, computes the address, and stores that instead of the actual value, which is stored at it. So it's basically store the pointer instead of dereferencing the pointer and then storing it. But yeah, back to this indexing. RDI is at the base here, and then we have to go past 6 bytes. Like we're gonna 3 times the size of the data, which is 2 each. Then we get up here. Right, so then we execute that, and we get indeed these bytes from here into RAX. But we don't want to hard code the exact byte offset into the array in each instruction. We want to be able to parameterize this in some way. We want to have another register, which is the index. We have one for the base pointer of the array, and then one for the index. Because then we do what we do in C and C++. We just like have the square brackets and we have the index. We don't need to compute the actual address of the byte inside of it, right? So let's use RSI as our index register and start it off at 0 to get to the 0th element. So we put 0 into RSI. And then we have a bit more of a complicated instruction here, because the address is now RDI, which is the base, and then the index times the size of the element, which is 2. So each element is 2. And then we multiply it by 0 to get at the 0th element. So then we just get to RDI. And RDI has A8. That's over here. So we move that into AX. So if we execute that, we get those 2 ones from here into RAX, into AX, the lower part of RAX. And then we can increment our index register. So RSI is our index. We increment that and get the value 1. And what's really nice now is now we have exactly the same instruction down here as we had up here. We've just parameterized it over the index. So now we can do all sorts of jumping around and stuff with it. We don't have to like rewrite this single instruction. It will be the same. You can it's just been parameterized by the index. So if I do this again now, this time RSI is 1. So 1 times 2 is 2. So we have RDI, which is pointing over here, and then we add 2, we get over here, and we execute that, and now we get the second element into RAX. And yeah, what's the difference between what gets moved if we dereference as a word versus a keyword putter? So a word putter is a 16-bit value. So we have to give, if you're going to put something into a 16-bit register, so you're going to put it into AX, then you have to give it a word putter, which is compatible. Both are 16 bits. If I want to put something in RAX, which is a 64-bit value, then I'm going to use a keyword putter. Yeah, these names of the registers, they are predefined by the architecture. So we have a bunch of these registers in the CPU, which are named, RAX, RBX, RCX, RSI, RDI, RSP, RBP, stuff like that. So you can't choose those. Lots of questions. What are all the registers? I think I have a bonus slide at the end with the list. Otherwise, we can get back to it later. Right, where was I? So we have parameterized, our instruction here. This one, oops, it's now the same. And that sounds like something you would use in a conditional or in a loop or something. So that brings us over to the next slide, which is going to be conditionals. So we say we want to have an if statement. We want to compare a couple of numbers, and we want to see if one is larger than the other. And if it is larger, we're going to store true somewhere, and if not, we're going to store false somewhere. So it's just a really simple example. So let's first get some values into the registers, putting 3 in RDI, 2 in RSI. So we have 2 values that we can compare. And then I'd say compare RDI and RSI. And assembly does not have any nice stuff like if or else or anything like that. It just has comparisons. And then it has goto, basically. And goto is considered awesome, right? So with some conditional jumps, goto, and comparisons, you can basically do whatever. So when I compare RDI and RSI here, I'm going to compare these 2 numbers, but nothing seems to happen. If I just execute that line, nothing changes that we can see here in our general purpose registers. The only thing that happens is that these 2 numbers get compared in some way, and then some metadata about that comparison gets stored away in some flags somewhere in the CPU. So the CPU now knows a bunch of stuff about that comparison, but nothing really happened. And then what we can do is we can use conditional jumps. So the next instruction here is JG, which stands for jump if greater. So that means now the CPU can go and look at the metadata from the previous comparison, and it can see, well, was the first one greater than the other one? And if it was, I'm going to jump to the greater label. And then let's jump down here. That's what's going to happen. We jump down to the greater label, which says move RAX1. And that's just me deciding I want to store true if the first one was greater. So I put the value 1 into RAX and just decided RAX is going to be where I put my results. So I just put 1 in there for true. And then someone has a nice suggestion that the R is for really extended. Yeah, that's a good it's a good suggestion. You got the EAX for the extended AX, and then I guess RAX could be really extended AX. Yeah, and then of course there's a bunch of other registers as well for the AVX and like all of those extra stuff, but we're not going to look at that in this talk. But there's someone posted in the chat a list of all the register names, the 16 general purpose ones. So thanks for that. Right, but back to the example. So that was when the first one was bigger. Let's just do the same example again, just with switches around. So now we have 2 in RDI, 3 in RSI, and then we do the same comparison again. So we compare RDI with RSI and nothing happens. We don't see anything, just those flags somewhere have been updated. So now I can do jump if greater again, JG, jump greater, and I can jump to the greater label if it was greater. But this time it was not greater. So then I don't really do anything. I just continue with the next instruction. And the next instruction will then be putting 0 into RAX. So I've decided that RAX is my result, so I'll put false or 0 in that one. And now I have to be careful, because if I just keep going here, I would fall into this one and also store true. So I have to now do an unconditional jump and jump out to the end of the entire if thing here. And then you can see that you did a comparison here, and then this was kind of our else block, and this was kind of our if block, and that's something you will quite often see in assembly. You have like the conditional, and then you kind of see that the else block is above the if block, which can be a bit confusing sometimes. And someone is like Googling the history and everything. So yeah, look in the chat if you want more of that stuff. I'm gonna ignore the chat now for a little while, I think, and go, yeah, talk a bit about the various types of comparisons. And CMP is just the single comparison thing. We just compare these two and all the metadata gets stored away. And then afterwards, you can decide what to do. So you can jump if equal, you can jump if not equal, and you can jump if it was less or equal, greater or equal, all nice stuff like that. But I said earlier that assembly doesn't have types. It just have bytes, right? So if I want to compare these 4 bytes with these 4 bytes, well, how do I interpret these 4 bytes? Are they to be interpreted as signed or as unsigned or whatever? The comparison doesn't know. So we have to, in our conditional jumps, decide whether to interpret the results as if they were signed or unsigned. And all the less and greater names were taken. So for unsigned ones, we have these other names below and above. So we have jump below for unsigned, jump above for unsigned, jump above or equal, etc. for the unsigned comparisons. So that's how the conditional jumps work with signed and unsigned types. And how does the compare instruction really work? Like I just said, it compares them and stores away some metadata. The comparison is actually just subtract. So it's going to subtract the second operand from the first. So CMP up 1, up 2 is basically doing operand 1 minus operand 2. If these are equal, then the result of that subtraction will be 0, and then the 0 bit gets set. So the 0 flag gets set if they were equal. If operand 2 was larger than operand 1, that's going to be a negative number, and then the sign bit gets set. So when I want to implement these instructions down here, jump equal, then I can just see, well, is the 0 bit set? If I want to implement jump greater, I can just see, is the sign bit set? Because the subtraction ended up with a negative value. So that's how that works. The chat is getting a bit crowded. I'll look at the Q&A thing. That one I've done. That one I've done. That one I've done. Yeah, the greater label, is it provided by the hardware manufacturer, and where are the labels defined? And that's actually a very good question. I just did a talk at the NDC TechTown last week where I talked a lot more about that stuff. The labels are just there in the assembly code. The labels are not there in the actual machine code. In the machine code, you have addresses instead of labels. So if we just go back to the previous slides here, these labels, they don't actually end up in the machine code. In the machine code, these will be addresses, memory addresses to jump to. So just the instruction pointer is pointing somewhere, and the instruction pointer then just says, okay, point over here instead. That's how that works, very quickly explained. Yeah, so now we have variables, arrays, we have memory addressing, we have conditionals, and the next thing then is to do loops. And assembly doesn't have if and else and that nice stuff like that. And of course, it doesn't have for or do or while or anything like that either. So what do we have at our disposal? We still have these comparisons and the conditional jumps. So compare and go to. So let's implement a quick loop in assembly. We are going to use RCX as our loop variable. So we'll initialize that one to 1. So that's basically just starting our counter at 1, and we're going to count up. I want to also put, so let's do that. We have 1 here. So this is our loop counter now. And I'm going to accumulate a value in RAX. So I'll just zero out RAX. It's already 0, but let's just do that. And then we go into our for loop. And the counter is now at 1, and I'm comparing it to 3. So basically, this is the part of the for loop where you say, is it equal to 3 or not? So we just compare, nothing happens when you compare, then you jump if they were equal. So RCX was 1, it's not 3, so we don't jump. And then we have add REX, RCX, and that's just, I had to come up with some sort of body for this little for loop. And my body is just adding the loop counter to RAX every time we go around the loop. So I just add RCX to RAX, which then turns into 1. Then I increment RCX, so I increment our loop counter to 2 and jump back to the beginning. So jump is an unconditional jump. I always do this jump. Back to the beginning of the for loop. Are we 3 yet? No, we're 2. So we do not, it's not equal, so we don't jump. We keep adding our loop counter to REX just to have something to do. Increment the counter, jump to the beginning of the for loop. Are we 3 yet? Yes, this time we are 3. So jump equal will actually jump to the end of the for loop, and we are done. And if you want to translate this into some C code, well, this is how it would look like. We have our move RAX 0 at the top here, which is just our variable to accumulate a result. And I just noticed I have a little, kind of a little bug here. I'm saying int RAX, so I guess this would be long RAX or int EAX. So I'm mixing up the types of it. Anyway, that's not really important. Then we do for int RCX equals 1. So that's this thing, put 1 into the counter. And RCX not equal to 3. That's this compare and jump if equal. And then the inc RCX is the plus plus RCX part. And then our loop body is just RX plus equals RCX. That's this add here. And then I guess you can see these labels as basically the curly braces here in the for loop. Just there are the labels that we jump around to. All right, then we have loops as well. So let's have a look over at Compiler Explorer again and have a look at a function. And everything gets a lot messier with all these Zoom webinar windows. So I'll just get those out of my way. So yeah, let's have a look at this little sum function here. Just a function called sum. It takes 2 parameters, a and b, 2 ints, and returns the sum of those as another int. Okay, sum a and b, return a plus b. So here is what GCC 11.2 decided to generate for the sum function. So if we go back to our slides again and just copy all of that in here, then this is exactly the code that was generated on Compiler Explorer by GCC. And now we have quite a few more registers that GCC decided to use. So the compiler is very free to decide which registers to actually use. And that's one of the important things of designing a compiler is that you have to make sure you are smart when you select which registers to use for what. But the first question to ask really is, how do you get those arguments into the function in the first place? So I'm going to call sum with a and b, but where do I put a and b? How do I get them into that function? And that's up to the calling convention. And I'm on Linux, or at least the talk was written on Linux. I'm on a Mac now, but I think they both use the systemv AMD64 calling convention. So that's or the systemv AMD64 ABI rather, which has a calling convention which specifies this stuff. So that's just an agreement about how to get stuff in and out of functions and other things like that. And on Unix, I think it's the same for all the Unixes. They have this calling convention, and then Microsoft has a very similar one. So how do I get 2 ints into a function? The calling convention says that, well, you can just leave them in a couple of registers that we've specified for this. So the first 2 ints go in RDI and RSI. And that is a really, really smart thing to do, because I am over here doing some computations. I have the values in the registers, and I want to call this function over here. I don't want to have to put that into memory and then call the function and then get it out from memory again. I can just leave them in RDI and RSI, call that other function, which just keeps on computing on those values in the registers. That's a really fast and nice way to get some ints into a function. So let's, if you see here, I have already filled in 2 and 3 for RDI and RSI, because whoever called the sum function will have put, and say they wanted to compute the sum of 2 and 3, they will have put the 2 and the 3 into those registers that the calling convention specifies. And then we get on with our function implementation. And the first thing we do is to push RBP. And that's because the calling convention also specifies which registers am I allowed to overwrite and which registers do I have to preserve. So I need to preserve RBP so that I don't overwrite my caller's value for RBP. So just push it onto the stack, and then at the end of the function, I can pop it again. So we have restored it and not overwritten it. And that's nice because the next line, the very next line here, we're actually messing around with RBP. We're taking a copy of RSP into RBP. So RSP is our stack pointer. We copy that into RBP. So now I'm visualizing both RSP and RBP here. And that's because RSP, when we start the function, that's the beginning of our stack frame. But we might mess about with RSP during our function. We could like push stuff onto the stack. We could call other functions. What could happen to RSP? So if we just make a copy of RSP into RBP first, then we have a stable base for our stack frame that we can use all the time. And it's not important in this example because we're not actually moving RSP, but GCC decided to do it just to be safe and or just by default. And on higher optimization levels, this will of course go away. Right. Then GCC decided we take EDI and ESI, our two parameters, and put them into memory at 4 and 8 away from RBP. So if you just run those two lines, this is our A and this is our B over in memory. And then it takes those two values from memory, RBP minus 4, RBP minus 8, and put them into EDX and EAX for some reason. Let's do that. We have them back here in registers. Then it decided, okay, now we can add them. Now we add EAX and EDX. And as we saw before, we get the result in the first register. So we get the result in EAX. So if you do that, 2 plus 3, and then the result is here. And now we're about to return very soon. But first we have to figure out how do we get that value out of our function again. And again, the call convention comes to rescue and says, you're just going to return a simple integer. Leave it in RAX. Don't mess about with the memory. When we get back to the caller, they can just keep computing on that value because they know you will have left it for them to find in RAX. So then we need to pop RBP because we pushed it at the beginning here. So we restore it for whoever called us, and then we return. And when we return, we just return execution to wherever we were called from. All right. Some people keep raising their hands. So yeah, if you want to ask a question, there's a separate Q&A thing where you can type in your question, and I will read your question and answer it. All right, then we figured this was a bit cumbersome to just like all of this work here just to add to ints. So what if we try to give it 02 or 01 or 03? Doesn't matter. Anyway, whatever you give it there, it's a lot shorter. It's just one instruction and a return. So this is LEA, the load effective address instruction that we saw earlier. So what's this instruction doing here? That was supposed to like load an address, right? That we needed to compute some pointers or something. Well, turns out LEA is really great at doing quick, simple math like this. And it has one big advantage over the normal add because you can do some arithmetic here and then store the result in a separate register. So I can just, with one instruction here, I can add RDI and RSI, our first two int arguments, and leave the result in EAX directly, which is the return register. So then I don't have to move the answer into the return register. So just one simple instruction, and then I return. So that's quick and simple like that. Yeah, so then we've seen variables, memory, arrays, control flow with loops and if. We've started looking at functions, and we also need to know how to call a function, because when we do that, then we can get to basically the holy grail of programming paradigms, which is, of course, procedural programming. So let's have a look at some procedural programming. Here we have two functions. We have one really simple one called ×2, which just takes one argument or one parameter and just multiplies it by 2. So the times 2 function takes an int, returns that int multiplied by 2. Then we have another function called sum times 2, which takes 2 ints, a and b, adds them together, and then returns that times 2. So it takes a plus b, passes it to times 2, and then returns the result. So a plus b times 2. And that's all of that assembly over here. So now we're going to take all of that and copy it back into our little slideware emulator here. And to do that, I'm going to need a bit more stack. And if you remember, the stack was growing down like this from the top. And I've just like continued the stack over here just to have enough room. So the stack just grows down here and then keeps growing down on the other side. So let's just get started with the sum times 2 function. Because I'll get back to that question soon that we got here. So the first thing we do is push RBP. We already know why, because we have to preserve it in case we overwrite it, and we do overwrite it because we say move RBP RSP. And that was to get a stable base pointer, because we might change RSP during execution of the function. And in this example, we are going to change RSP. So then it's really nice to have this stable backup kind of in RBP. And that's the next instruction, which was also asked about in the chat. Why are we subtracting 16 here from RSP? And RSP is the top of the stack. So when we call another function, they need to be able to start using the stack from that point. So we need to set aside some space on the stack for our own purposes. So GCC decided we want to have 16 bytes for our stack frame, which is ours. So let's subtract 16 from RSP, and you can see now the stack pointer is here. So the next function can then start from here using that as their beginning of the stack. Why we got 16 exactly, I am not sure about, because we are only going to be using 8 bytes of this stack frame in this function. But GCC decided to use 16. And 16 can change if you change stack alignment. Yeah, so there might be some alignment requirements on the stack. I'm not too sure about the details there. So there might be some minimum number of bytes you have to align to. But yeah, just as we saw before with our simple sum function, we then take EDI and ESI, and which are our 2 parameters, and put them into the stack here. So now we do that RBP minus 4 and 8. So that's over here. So we execute that, we get 2 and 3, get our arguments into the stack. So again, we assume someone called the sum times 2 function with the arguments 2 and 3. So whoever called us would have put 2 and 3 into RDI and RSI. And the nice thing about actually putting these into memory instead of just leaving them in the registers is that now we have L values. Now we can take the addresses of these 2 parameters. So if we want to take the addresses, now we can actually do that. If we don't do that, then we wouldn't have needed to put them into memory. But now we can take their addresses, their L values, we can see them in the debugger, and so on. And then we move these back into memory, just like we did before. So we take these 2 values, put them into EDX and EAX. So we get the 3 here and a 2 here. And sometimes 2, the first thing it does was to just to add the two parameters. And the result then ends up in the first operand, which is EAX. So here we have the value 5. Right, then we can, now it's our turn to call another function. So now it's our turn to call times 2 int. And then it's our turn to fulfill like our part of the agreement that we have to put the first int argument into EDI. So we have the 5 that we got from this addition. We need to put it into EDI. So let's execute this, move EDI EAX. Then we have our 5 here. So that's the argument to call times 2. Then we call times 2. So the instruction pointer just jumps down here, and we push RBP, move RBP RSP. We've seen it many times. We take EDI and put it into our stack frames. Now we can see RBP is pointing down here. So now our part of the stack starts here for this times 2 function. So we take the EDI parameter, put it into memory here. So we have this value 5. And then we move it back into EAX for some reason, which is unknown to me. But then we are going to multiply. The times 2, remember, took the parameter, multiplied by 2. And even on O0, GCC decided I'm going to just add it to itself because it's faster. I see there are more questions. I don't think I have time. You were quite a chatty bunch, which is really nice, but there's just 5 minutes left, so I'm going to ignore the questions until the end now. So GCC decided, well, to multiply it, I just add it to itself. So add EAX, EAX. So 5 plus 5 equals A. And we get the A in RAX. And that's really handy because RAX is, or EAX, sorry, that is our return register. So that's where it's supposed to be. So we don't need to move it anywhere. We can just pop RBP. So we get back our RBP, and then we can return back to the caller. Right, and then we're supposed to return this value. And like we know that the last thing we did was to call times2 int, which would have left our value in RAX or in EAX, sorry. So we don't have to move it anymore around. It's already in the place where we want it to be. And then we're going to do the leave instruction. And the leave instruction is going to do 2 things. So I'll visualize it in 2 steps here, even though it's just 1 instruction. Leave is going to restore both RSP and RBP. So first, it's going to restore RSP. And how do we restore RSP? Well, we subtracted 16 from it here. But the last thing we did before doing that was to copy it into RBP. So we can just copy RBP into RSP. Let's do that. Now we have restored RSP. And then we do the thing we always do to pop RBP to restore it for whoever called us. Off it goes. And then we can return control to our caller. Why did times2 not subtract 16? Because it didn't call any other functions. So if times2 called another function, it would have had to subtract from RSP to save space for ourselves and like set aside something from where the next function could pick up. But it wasn't calling any other function, so we didn't have to do that. Yeah, so then we return, and that's it. And let's just, again, try to put on some optimizations here. That's a lot better. So this is really optimized quite a lot. So you can see it matters, the optimization flags. If you look at the times2 function, it's just taking an int and multiply it by 2. So it's using the load effective address thing again to just take the first parameter, add it to itself, and store it into the return register. So a really, really quick way to just 1 instruction multiply by 2 by using an addition and getting the result in the right place. And then if you look at the sum typing, well, it's adding EDI to ESI using the add instruction. And that's also handy because then we have the result in EDI, which is the first argument that we were supposed to pass to times2. But we haven't even called times2. We've just inlined the times2 function in here. So we see the exact same LEA instruction, which is using to then add this number to itself and returning it. And if we would then just move the times2 function up here to the top and make it static so it gets internal linkage, the entire times2 function just goes away. It's not even in the object code. Right, and then finally, it's time to return to our first example on Compiler Explorer. And I promised you that you would understand everything on this side. And now we actually do understand everything. I was planning to read through actually all of these lines, but we are running out of time because it's got a bit more interactive than I was planning for, but we can quickly just go through it. We have push RBP, move RSP RBP, which is the stack preamble thing. We can see that it's taking the 2 first parameters in EDI and ESI, putting them into memory. Yeah, so this is for the computer function here. I have a for loop, which is done by just some comparison and jump if not equal. And yeah, move, add, yeah, actually, I don't have time to go through all of it, but this is all stuff we have seen on the slides so far. And if there's something, I'll post this link in the chat later. But if there's something you don't understand here, you could always also just hover over the instruction and get some more tips. And speaking of tips, first thing to do if there's something you don't understand on Compiler Explorer, hover over the instruction and see if you get a hint, and then you can search and find out more. If you want to try it with your own code, then make a local standalone reproduction. So try to get everything into one CPP file locally, which compiles, which has no includes, and just inline everything. Maybe your compiler or your IDE can help you with some inlining stuff. Make a local standalone reproduction. That will make it a lot easier. But Compiler Explorer has a bunch of libraries. So it has Boost, Catch2, it has FMT, it has Eigen, a lot of useful stuff. So you can actually use those libraries there, and that can be very useful. And when you start, try to do as in this talk and use ints instead of complicated types, and then you can rather fill in your own types later when you understand like the fundamentals around it. And of course, don't try it on your full project. It's meant for figuring out like small specific things. And that's it. I'm going to spend a few more minutes in here answering if there are any further questions. And then a few minutes after that, I'll be in GatherTown in the track A room in GatherTown, and we can chat a bit more if you have any other things you want to like, if maybe you have some tips for the others or anything like that. All right. There was one more question in the Q&A thing. If a function has multiple arguments, how do they get mapped to RDI, RSI, and other registers? The first 6 ints go in RDI, RSI, or EDI, ESI, EDX, and then I don't remember the last, but you can look it up. If you have more than that, or if you have something big which doesn't fit in a register, then you push it onto the stack. So then the caller is going to push it onto the stack first, and then the callee will have to look back up into the caller's stack frame to find those values. Then thank you, useful. Thanks for the talk. Thank you for coming. I appreciate if someone found it helpful. Yep, I think that's actually, yeah, that's it for questions for now. So then I just say thank you to everyone who came and everyone who made this a lot more interactive than I hoped, or I thought, which is great because I really like to talk to an actual audience and like get questions and answers and stuff. So that was super nice. So thanks for all your questions as well.